Assalamualaikum viewers, my name is Varisha Kawal and my registration number is 16TE86. This is lecture 6 part B of week 5 and today's lecture is about as I already told you in previous lecture about the names of the types of the decomposition: impulse, Fourier, step, even, odd and interlaced. Now I explained it one by one. So first is impulse. Impulse decomposition. Impulse decomposition is in which it breaks and samples signals into n component signals, each containing n pulses. Each of the component signals contains 1 point from the original signal, with the remainder of the values being 0. So a signal non-zero point in a string of zeros is called impulse. Impulse decomposition is important. Why? It is important. Why important? It is important because it allows signal to be examined one sample at a time. Similarly, systems are characterized by how they respond to impulses. How they respond to impulses. By knowing how the system responds to an impulse, the system's output can be calculated for any given input. This is called convolution. Convolution is actually multiplication of the impulse by its shifted version. That is, the system's output can be calculated. System output can be calculated from any given input. Next is step decomposition. After this, I compare these two compositions by example. Step decomposition also breaks n samples into n components signals. Each composed of n component is a step. That is, the first sample have a value of 0, while last samples are some constant value. Now consider the example. Consider the decomposition of n point x of n into the components x1 of n, x2 of n, up to so on x of n minus 1 of n. So the kth component signal xk of n is composed of zeros for points 0 through k minus 1. While remaining points have a value of x of k minus x of k minus 1. For example, the fifth component signal x5 of n is composed of zeros for points 0 through 4, while the remaining samples have a value x of 5 minus x of 4. Now I explain it through graphs. This example, in impulse decomposition, the signal is x of n, which is like this, and the same signal is used for the step decomposition. So in impulse decomposition, x naught of n is this, but in step decomposition it is like this, x naught of n. x1 of n in impulse is, but in step it is like this. So as a special case, x naught of n has all of its samples equal to 0, just as impulse decomposition looks at a single one point at a time. Step decomposition characterizes signal by the difference between the adjacent samples. Likewise, systems are characterized by how they respond to a change in the input signal. Then next type of decomposition is even odd decomposition. That is, a signal breaks into the components, one having even symmetry and the other have odd symmetry. Signal having even and odd symmetry. Even if I have a signal like this, then it is even, because before 0 and after 0 same shape. But in odd signal, one side is the reverse of the other side, that is odd. And the formula for even is x of n plus x of n minus n divided by 2, and for odd we placed negative sign instead of plus, divided. We can solve the example by these two formulas. Then next is interlaced decomposition. In interlaced decomposition, it breaks the signal into the two components, the even sample and the odd sample. To find the even sample, start with the original signal and set all of the odd number samples to 0, Actually, in this decomposition, we see the indexes, not the amplitudes. Indexes are important, not amplitudes. For example, x of n is equal to 1, 2, 3, 4, 5. So here xe of n is 0, 2, 0, 4, 0. Here 2 is even, 4 is even. So I place 0 in odd places. 1 is odd, 3 is odd, and 5 is odd. But in odd cases, I have 1, 0, 3, 0, and 5. Next is Fourier decomposition. Fourier decomposition. In Fourier decomposition, it is very mathematical but not very obvious. Any n point signal can be decomposed into n plus 2 signal. Half of them sine waves and half of them are cos waves. The lowest frequency cosine wave is in this makes 0 complete cycle over the n sample, and it is DC. The next cosine components, and this pattern holds for the remainder of the cosine waves as well as for the sine wave component. Since the frequency of the each component is fixed, so the only thing changes for the different signal being decomposed is the amplitude of each of the sine and the cosine wave. So in this decomposition, amplitude of sine and cos waves changes. It is important for 3 reasons. Firstly, a wide variety of signals are inherently created from superimposed sinusoids. Audio signals are the examples of this. Secondly, linear systems respond to the sinusoids in a unique way. Respond to sinusoid in unique way. And thirdly, most cutting-edge DSP's algorithms are based on the aspect of these techniques. Knowing how the system will react to the sinusoids allows the output of the system to be found. Third is the Fourier decomposition is the basis for the broad and powerful area of the mathematics called Fourier analysis, and even in advanced stage it is called Laplace and Z transform. Now next topic is about alternatives to linearity. Alternatives of linearity are if the non-linear system, if the system is non-linear, then consider it small. Small amplitudes make linear systems. If two systems are added, then change it into logarithmic scale. It also reduces the complexity. So this is all about the decomposition, types of the decomposition and alternatives to linearity.